In this video, we're going to finish up our discussion of topics from 3.5, and we're going to talk about elasticity of demand. Price elasticity of demand is what we're talking about here, and our formula for that is going to be eta, which I know looks a lot like a cursive N, but it's a Greek letter like that, is equal to the P divided by X divided by dP dx. So if you want to say the unit price, the price per unit divided by the derivative of the price function, the demand function. So let's go ahead and define a few terms here. So if the absolute value of eta is equal to 1, then we call that unit elastic. If the absolute value of eta is less than 1, we call that inelastic. And if the absolute value of eta is greater than 1, we call that elastic. And this is related to if you were to look at the revenue function. So this would be when R prime is equal to 0, it would be unit elastic. You would have a flat revenue curve. This is if R prime is is less than 0. And this is if R prime is greater than 0. We'll see when we look at our curves here, our revenue curves. So let's go ahead and get started here with number 27 from the textbook. And 27 is that my demand equation P equals 600 minus 5x, and the x value we're interested in here for demand is 60. So P divided by x is going to be 600 over x minus 5, and dP dx is going to be -5. So eta is going to be 600 over x minus 5 over -5 is a -120 over x plus 1. And so I want to now find eta at 60 units. So -120 over 60 plus 1 is a -2 plus 1 is a -1. So the absolute value of eta of 60 is the absolute value of -1 is 1, which means it's unit elastic. And if I look at the revenue curve here, R is equal to XP is equal to x times 600 minus 5x, will be the same as -5x times x minus 120. So I can sketch a curve here, a revenue curve that has zeros at 0 and 120, and it opens down, and halfway between there will be my vertex at 60, and it will be elastic from 0 to 60, and will be inelastic from 60 to 120. And we're unit elastic because we're right there in the middle between where it's elastic and inelastic. Let's look now at number 28. '28 has the demand equation, P equals 400 minus 3x, and our quantity of demand is 20 units. So P over X is 400 over X minus 3, and dP dx is -3. So eta is equal to 400 over X minus 3 over -3. That is, eta is -400 over 3x plus 1, and eta of 20 is -400 over 60 plus 1. Eta of 20 is -20/3 plus 3/3 is -17/3. And so the absolute value of eta of 20 is equal to 17/3 is definitely greater than 1. So this is elastic. And my revenue function so negative x times 3x minus 400. Let's pull that 3 out as well. Really doesn't make a difference, but it makes it easier for me to draw the graph. So I have 0, and I have over here somewhere, draw my curve right there. We'll call that 400/3. Right here in between, we'll say it's 200/3. It's halfway from 0 to 400/3. And so we are elastic from 0 to 200/3. And we're inelastic from 200/3 to 400/3. And 5 2/3 is over in this area over here. This is something bigger than 6 and less than 7. So we're in this region over here with a positive slope. So we were elastic. All right, let's look at number 29. '29 says P is equal to 5 minus 0.03x. X is equal to 100. So P divided by X is 5 over X minus 0.03. And dP dx is -0.03. Eta is equal to 5 over X minus 0.03 over -0.03. And let's see what 5 divided by -0.03 is. That is it's a fraction. It's -500/3. Okay. So eta is equal to -500/3x plus 1. And eta of 100 is negative 500 over 300 plus 1. So that's going to be eta of 100 is negative 5/3 plus 3/3 is negative 2/3. Absolute value of eta of 100 is 2/3 is less than 1, which is inelastic. My revenue function here, R will be equal to X times 5 minus 0.03x. And so R is negative 0.03 x times x minus 500 over 3. I already did that division up here of 5 divided by negative 0.03. So here's my sketch, what that will look like. 0 to 500 over 3. Right in the middle here is 250 over 3. And so we are elastic from 0 to 250 over 3. And we are inelastic from 250 over 3 to 500 over 3. Look now at number 30. Number 30 has a demand function of 15 minus 0.0003x and a quantity of demand of 25,000 units. So P divided by X is 15 over X minus 0.0003, and dP dx is negative 0.0003. So eta is going to be 15 over X minus 0.0003 divided by negative 0.0003. 15 divided by negative 0.0003 is going to be negative 5,000. 50,000 over X plus 1. And that's eta of 25,000. It's negative 50,000 divided by 25,000 plus 1 is a negative 2 plus 1 is a negative 1. So absolute value of eta of 25,000 is equal to 1, which is unit elastic. And my revenue function here will be X times 15 minus 0.0003x. So R is equal to negative 0.0003x times X minus 50,000. And my sketch here will be 0 to 50,000 with 25,000 here in the middle. And so we are elastic from 0 to 25,000. I'm not putting commas there because the comma is my separator between my initial and final value. Inelastic from 25,000 to 50,000, like that. Move on now to number 31. And no longer are we going to have nice demand or revenue curves that are parabolas that open down like that, because we're going to have nonlinear demand functions. So we have 31 gives us our demand function P for price is equal to 500 over X plus 2. And our given demand quantity is 23. So P divided by X is 500 over X times X plus 2. I'm just going to leave it that way. And dP dx is going to be negative 500 over X plus 2 quantity squared. So eta is going to be 500 over X times X plus 2 divided by negative 500 over X plus 2 quantity squared. So eta is going to be 500 over X times X plus 2 times X plus 2 times X plus 2 over a, I'll put the negative up there, 500. 500s will cancel. One of the X plus 2's will cancel. Eta is a negative X plus 2 over X. And then eta of 23 is going to be a negative 25 over 23. And so the absolute value of eta of 23 is equal to 25 over 23 is greater than 1. So this is elastic. And my revenue function here, it's going to be 500 X over X plus 2. To draw a sketch of that, I'll need my calculator. 500 X over X plus 2. And zoom 0 here. And so it's going to go through 0, 0, and it's going to go up like that. I'm only interested in that positive portion of the graph. It's like so. 0, 0. It's like that. And so it's always going to have a positive slope there. So it's elastic from 0 to infinity, like that. (32) is the demand function P equals 500 over X squared plus 5. And our given demand quantity is 5. P over X is 500 over X cubed plus 5 over X, which is going to be 500 plus 5x squared over x cubed. And dP dx is negative 1000 over x cubed. So eta is equal to 500 plus 5x squared over x cubed divided by negative 1000 over x cubed. So eta is equal to 5 times x squared plus 100 over x cubed times x cubed over 1000, and that's negative 5 goes into 1,200 times. X cubed cancels out with x cubed and gives me a 1. So eta is a negative x squared plus 100 over 200, like that. And eta of 5 is a negative 25 plus 100 over 200 is a negative 125 over 200. Eta of 5 is negative 5 over 8. Yeah. So absolute value of eta of 5 is 5 over 8 is less than 1. So that's inelastic. And let's go ahead and look at what the revenue equation would be here. It would be 500 over x plus 5x. So 500 over x plus 5x. And it's going to come down and go up like that. I'm going to do a little better here because I know that the equation of the asymptote here is the 5x. So it's got a line that goes like this. I know the vertical asymptote is at x equals 0. So it's stuck in this little region right here. And so I'm going to find this minimum value. I'm going to zoom out just a little bit. Zoom out. And I want to find second calc minimum. We could do this with a derivative if we want to, but we've got the calculator. So somewhere in there. And it looks like it's at 10, 100. So our demand is inelastic from 0 to 10, and then elastic from 10 to infinity. Let's move on to number 33. Number 33 gives us a demand function of P is equal to 20 minus 0.02x. And we're given the restriction here that x has to be between 0 and 1,000 units. And that's just simply because after 1,000 units, our price becomes negative, and that doesn't happen. So we don't want our price to go below $0. We don't want to go below $0 the other way either. So that restricts us to be between 0 and 1,000 units there. So we want to determine when the demand is elastic, inelastic, or unit elastic using our techniques that we've been using so far. So 20 over x minus 0.02 is our p over x, and our dp dx is negative 0.02. So eta is going to be 20 over x minus 0.02 over negative 0.02. Back out here, 20 divided by negative 0.02 can give me eta is negative 1,000 over x plus 1. And so I'm going to find the absolute value of eta. It's the absolute value of negative 1,000 over x plus 1. And I want to set that to 1 to find out where it's unit elastic, where it changes from being elastic to inelastic. So that means that negative 1,000 over x plus 1 is equal to 1, or negative 1,000 over x plus 1 is equal to negative 1. Well, if I had this situation, 1,000 over x would have to equal 0, which can never happen. I can't divide 1,000 by any number and get 0. I can get close to 0, but I can never get there. So I have to have this situation over here. Negative 1,000 over x is equal to a negative 2, meaning 1,000 over x is equal to 2, which means 2x is equal to 1,000 and x is equal to 500. So 500 is where it becomes unit elastic there. So the demand, this is my answer for part A, is unit elastic of unit elasticity when x equals to 500 units. For x values in 0 to 500, including 0, the absolute value of eta, I plugged 0. If I could plug 0 in there, let's see, I would get a absolute value of negative infinity, which would be infinity, which would be positive. That's greater than 1. So demand is elastic. For x values in the interval of 500 to 1,000 included, sticking 1,000 in there would give me negative 1 plus 1 is 0, which is less than 1. It's less than 1. So demand is inelastic. And then part B asks me to use the results from part A to describe the behavior of the revenue function. So we should be increasing on the interval of 0 to 500. We should be flat at x equals 500, and we should be decreasing on 500 to 1,000. And those are all, I guess these are closed as well, so that they match these other intervals. Let's look at number 34. 34 gives us the demand equation P equals 800 minus 4x, with the restriction that x has to be between 0 and 200 included. And so we want to find again where this is elastic and elastic, unit elastic. So P divided by x is 800 over x minus 4, and dP dx is -4, making eta equal to 800 over x minus 4 divided by -4 will be -200 over x plus 1. Absolute value of eta is the absolute value of -200 over x plus 1. And so that means, and I want to set that equal to 1 to find out where it is unit elastic. It's -200 over x plus 1 is equal to 1, or -200 over x plus 1 is equal to -1. And this doesn't make any sense. So we ignore that one. -200 over x equals -2. And we have -2x equals to -200. X is equal to 100. So we'll be unit elastic, x is equal to 100, will be elastic when, let's see, when x is less than 100. So 0 to 100, and will be inelastic when the 100 to 200 included. So looking at my information from part A here to answer part B, we'll be increasing on the revenue function 0 to 100, and will be flat at x equals 100. That'll be my maximum revenue, and will be decreasing from 100 to 200, and that gets included. All right, that's it for this video, and I'm going to wrap up the section there, even though there's lots more problems to try. All of them from this point on are mostly calculator problems that they want you to use the minimum and maximum feature of the calculator to help you find minimum or maximum values. And I just hope you can do that now, as we've shown that a few times here. It's in the second calc menu, and your minimum is number 3 and your maximum is number 4. You need to cut out a little interval using the left and right arrow keys. Hit enter to put a tick mark on the left, and arrow over to the right, put a tick mark on the right, come back and make your guess. And I just will leave those for you to do. If you have questions about those, feel free to ask about them specifically, or come in and see us for tutoring if you're a Reynolds student, and we'll be happy to help you, or set up an appointment through Navigate. If you're a Reynolds student, we can help you with that with the calculator. But I'll leave you to work those out yourself with your teacher or with your tutoring center for your college or university, wherever you're at. All right, that's it for this section. We'll come back next time to start talking about 3.6, which covers asymptotes. So see you for the next video.